Okay, everybody, we're going to take a look at vector addition using what's called the method of components. We've already showed you how to add vectors graphically head to tail. Now let's show you how to do it mathematically with this method. It involves things you already know how to do, just put into a kind of a cookbook way of doing it. And there's 4 steps basically. Number 1, you will resolve your forces into x and y components, as we've done in the past. If you have x-axis angles, the x component is a cosine theta, the y component is a sine theta. If you have y-axis components, y-axis angles, the x component will be a sine theta, and the y component, ay, will be a cosine theta. Second thing, once you resolve off-axis vectors into parts, then you're going to add all the x components algebraically to obtain the x component of the resultant. In a similar manner, you're going to add all the y components algebraically as well to get the y component of the vector sum, which is ry. And the formula we're showing you here is that the rx component will be the x part of A plus the x part of B plus the x part of vector C. Now the other way you could write that is that Rx would equal, if we're talking force vectors, Rx would equal F1x plus F2x plus F3x, and if there are more to add, there will be more there in your formula. In a similar manner, the y component of the resultant, Ry, would be F1y, would be the sum of F1y plus F2y plus F3y, and if there are more to add, you'll include them in your equation as well. Once you get the x and y components of the resultant, Rx and Ry, number 3 says that you will draw a head-to-tail sketch of the x part plus the y part to construct vector r. And you'll form a right triangle basically when you do this, because Rx and Ry will be perpendicular. Finally, once you draw that right triangle, you're going to use, you're going to find the magnitude and the direction of the resultant using, this stands for the magnitude, r in the absolute value signs, and that equals the square root of the quantity Rx squared plus Ry squared. You may recognize that as the Pythagorean theorem, and the magnitude r here would be the hypotenuse of your right triangle. You also need to find the angle in the right triangle near point P, and that would be the inverse or arctan of opposite over adjacent, which would be Ry over Rx. So let's look at a problem and try to find the solution using this new method. Here we have the problem. We have 4 vectors, and you may find this familiar that we have 4 vectors that act on a common point, which would be point P, at the origin we'll call it. And notice that F1 is 125 newtons at 25 degrees below the negative y-axis. F2 is 130 newtons directly along the negative y-axis. F3 is 180 newtons and is 23 degrees below the positive x-axis in quadrant 4. And force 4, F4 is 150 newtons. It's in quadrant 1 and it is 62 degrees counterclockwise from the positive x-axis. So the first thing we want to do is break these forces into parts, and we're going to draw the parts as we've done in the past. And we'll start with F1, which is in quadrant 3, and we'll get first this part. We will get F1x, assuming that my pen wants to write. I'll try another pen here. We'll get F1x, and we'll get F1y. Now notice that these are pointing in the negative direction, so we've got to deal with signs now. This is an important feature we haven't had to do much with until now. So F1x is just going to be, it's going to be basically minus 125 times the cosine of 25 degrees. F1y will be minus 125 times the sine of 25 degrees. And of course those are newtons. The reason they're negative is because the x part points along the negative x-axis and the y part points parallel to the negative y-axis. Now if we move down to force 2, as you can see, force 2 is basically along the negative y-axis. So if we write this out, F1x, if we go to F2x, there isn't any part to it, so it's just 0. And F2y, it's along the negative axis, negative x-axis, so that's minus 130 newtons. Okay, now when we come over to F3, which is in quadrant 3, we're going to draw its parts. Let's use a different color here maybe. The x part will come over like so, and the y part will come down like so. They're perpendicular components or parts. And what we have here, this part right here, this is going to be F3x, which will be 180 newtons times the cosine of 23 degrees. And the y part, everybody, will be 180 newtons times the sine of 23 degrees. And by the way, once we do that, we eliminate the original vector, which I just crossed out. Finally, we have in quadrant 1 F4, and we're going to break it into its parts. And what we have here would be, we have the x component coming straight out like this, and the y component is straight up like so. And we'll put arrows on them to indicate the direction that they are in. Okay, and if you look carefully, F4y is going to be 150 newtons times the sine of 62 degrees, and the x part is going to be, that's F4x, it's going to be 150 newtons times the cosine of 62 degrees. So we replaced each off-axis vector with its parts and realized that F2 has it's completely a negative y component and no x component whatsoever. Next, what we're going to do is add them up. So Rx will simply be the sum, excuse me, sigma fx. We'll add up all the x components, and we'll keep the signs to add them algebraically. So when we do this, we will have the following. We will have, starting with F1, we will have minus 125 times the cosine of 25 degrees. We will also then have plus 0, excuse me, again, for F2x, and then we will then have, for F3x, we will have plus 180 newtons times the cosine of 23 degrees. It's positive because it's along the positive x-axis. And F4x is also plus 150 times the cosine of 62 degrees. Now when we work out all the trig and come up with a single number, you can do that on your own with a calculator, you would find that you would get 122.8 newtons. That's the x component, Rx, of the resultant. In a similar manner, we're going to want to find the y component of the resultant, which will equal the sum of all the y parts, sigma Fy. And going around with what we constructed earlier, we have for F1y, we have, this is minus 125 times the sine of 25 degrees. F2y is minus 130. F3y is also it's downward, so it's a negative also. It's a minus 180 times the sine of 23 degrees, and I just caught a mistake above it. 180 should be, this should be the cosine of 23 degrees. Glad I caught that. And then finally, the y part for F4y is upward, so it's going to be plus 150 newtons times the sine of 62 degrees. So we have minus 125 times the sine of 25 degrees, minus 130. And then we have minus 180 sine 23 plus 150 sine 62. When you work all this out on a scientific calculator, making sure you're in the degree mode, not the radian mode, you should find that you come up with a negative 120.7 0.7 newtons. Next thing to do is then to draw the x and y. You want to draw the head to tail diagram of Rx plus Ry to find the resultant. So what we're going to do is now we're going to look at how big these are. They're not too different in size, but we've got to be careful how we draw them. Rx is positive, so it will go to the right. So we'll start here. This is the origin, point P, which would be the same as the origin up above right here, where everything was concurrent. And this is 122.8 newtons. So we're going to draw, I'm just going to go over 4 blocks. Okay? And actually I'm going to go over one more. I'm going to go over 5 blocks. And that's basically Rx, and that's 122.8 newtons. And then we're going to put the tail of Ry at the head of Rx, and it's going to go downward. It's a little slightly smaller. So instead of 5 blocks, it's just going to be shy of 5 blocks, something right about like that. And that's minus 120.7 newtons. You have to construct this. You have to draw Rx plus Ry to really get a sense of what it looks like and what quadrant the resultant, will fall. It's going to be a quadrant 4 vector for the resultant. So I'm going to draw it. I'm going to turn the paper a little bit because it's just easier for me to draw it this way. Hope you're okay with that. And I'm going to I'll write it back the other way. So this vector, if I get my pen to work, this vector here is the resultant. This blue vector, if you can see it. I don't know if you can see the color or not. And we need to get the magnitude of the resultant. And we need to get this angle close to point P, and that's theta sub r. Okay, now we've got a right triangle, so the magnitude of the resultant is just the hypotenuse. So the magnitude of the resultant will equal the square root of the following. It'll be 122.8 newtons squared plus minus 120.7 newtons squared. And you're going to take the square root of the sum of the squares. And when you do that on a calculator, you should come up with 172.2 newtons. I'll leave it up to you to try that on your own to verify that. Finally, we need to get the directional sense of the resultant, which is theta sub r. And it's going to be the inverse tangent, or arctangent, to the minus 1. That's going to be the opposite over the adjacent. So the opposite is actually, it's a minus 120.7 newtons over 122.8 newtons. And when you do this on the calculator, you will find that you get a negative 44.5 degrees. Okay, now that's, if you know your tangent functions well, the tangent is negative in the, I believe, the second and fourth quadrant. Okay, so we have to think about how we're going to express this. So for the whole answer, what we have that the answer, if we put it all together, bringing these two down here, what we're going to see is that we have the resultant equals 172.2 newtons, basically at 44.5 degrees below the positive x-axis. So there's the method of components, the way it works. You break all the vectors into their perpendicular components. You add them algebraically, remembering that any vector part that is to the left is negative, and any vector part that is downward is also negative. So you have to watch your signs. So you have to draw this good enough that you can figure out whether the components are to be added or subtracted when you sum all the parts. You get the parts, you have to draw the head-to-tail diagram of the Rx plus the Ry, draw your hypotenuse of your right triangle, use the Pythagorean theorem, use the inverse tangent, and then think about what quadrant you're in, and then put your final solution, expressed magnitude and direction, all put together.